Okay, let's start class. Last time we started generalized linear models. And today we will continue to talk about generalized linear models. So I think we stopped here last time. We discussed the three components of generalized linear models. So we have a random component here. For the y is a random variable. We have some distribution, and that distribution cannot be any distribution. Some of them, it has to fall into a family that's called exponential family. Okay? And we have a systematic component. It can be looks like a multiple linear regression. So it's a linear function of the predictor variables. And the connection between the systematic components and the random variable y is through this link function. So link function is a function with the argument is the expected value of y. Okay, so it's a g function of expectation of y. So we can write as a g with the input is the expected value of the random variable y equals to this term, the systematic component. And the g function is called a link function. Okay. Now let's see the assumptions for the generalized linear model. So the first one, and which is the most important, that's the independence assumption. So the data points should be independently distributed. Okay? And the dependent variable y actually doesn't have to be a normal distribution, follows a normal distribution. It typically assumes the y follows instead of exponential family. Okay, an exponential family includes normal distribution as a special case, but also it can it includes several other distributions like binomials, Poisson. And GLM does not assume the linear relationship between the response variable and the explanatory variables. Okay, it assumes what? It assumes a linear relationship between the expected value for the response in terms of the link function g and the explanatory variables. So we can write the g mu. Mu is the expected value of y. So the g mu can be expressed as a linear function of x. Okay, so that's what GOM assumes. And the explanatory variable can be nonlinear transformed of some of the original variables. And the homogeneous or variance assumption, which required in the OLS, does not need to be satisfied. Actually, for some of the GOM models, if the homogeneous or variance is satisfied, that actually breaks the assumption, makes the assumption not hold. Because you will see it's actually, we have a link function. Let's say if the link function is nonlinear, like a log function, then it means the homogeneous or variance assumption does not hold, should not hold. If it holds, there's a problem. An error that needs to be independent to each other, but it doesn't have, it may not be normally distributed. And the parameter estimation in the GOM is not through the least square approach, but through the maximum likelihood approach. So we maximize likelihood function. Okay. So why exponential family? I've already explained that, because the principle behind the GOM is to unify several models into one very general framework under the exponential families, so that we can use the same estimation and inference to interpret and predict for all these models. Okay? But just keep in mind that some of the popular distributions, like a Weibull distribution, von Mises distribution, which used quite a lot in the survival and reliability analysis, does not belong to the exponential families. Okay, now let's see 3 examples. So the first one is the simple linear regression, which we all know. So for the simple linear regression, we assume the mean of the response, which is the expected value of the response, is a linear function of x, right? So the random component is what? Is the y that follows a normal distribution, with mean is mu constant variance sigma squared. Okay, and we know the PDF, the probability density function for the normal distribution is this one. And if you check this, the PDF for normal, you can easily find out this falls into the exponential families. We can write the PDF for the normal distribution in this form. So that can show that normal distribution is in an exponential families. Okay. And the systematic component is this one, is the linear function of x, right? And the link function is what? Link function for the linear regression is actually the simplest. Link function is the identity link. So that means the G mu equals to mu itself. Okay, so that's the identity link. So that's the simplest case for the GOM. Okay, the next one is the logistic regression. Okay? So logistic regression models the odds of success for a binary response variable. Depends on some explanatory variables. So we can write the logit function of the y, or the pi I. What is pi I? Pi is, so here, the response variable in the logistic regression is a binary variable. Let's say yi can have 2 possible values, right? Either 0 or 1. Okay, let's just say 0 is failure and the 1 is success. Okay, so what is the expected value of yi? The expected value of yi is what? Is the probability of yi equals to 1. Is that right? So that's the probability. Okay, so we can write the expected value of yi as pi I. So that is the notation I used here. So that's why it's logit pi I. So this is a link function. It's a g of the expected value of y. Okay. And what is the link function g? I expanded here is the log of pi I divided by 1 minus pi. And that is the logit function. So you can see the link function in the logistic regression is this one. Okay. And the random component y follows a binomial distribution. And this is the PDF. Actually, it's called PMF. Why it's PMF, not PDF? Because this is a discrete random variable. Okay, so for the discrete distribution, we call it probability mass function instead of probability density function. Okay, so this one you can check also belongs to the exponential family. Okay, so this is the logistic regression. We will see some examples in a minute for the logistic regression. Okay, but this just give you some example for the GOM models. And the last one is the Poisson regression. So Poisson regression is another popular generalized linear model, which is used to model the count data. Okay, so the Poisson regression models a discrete response variable, usually for the count, on a set of explanatory variables. Okay, so we usually use the log as a link function. Okay, so we have the log of lambda I. Okay, so what is lambda I? So here the yi is the count for the i's trial. Of course, it connects with some explanatory variables xi. Okay, so yi is the count. So the expected value of the yi, we call it lambda I. So lambda I is the expected value of the y. Okay, yi is the count. And you may ask why lambda I is used, because traditionally for the Poisson distribution, this is the PMF. This is a discrete distribution. The Poisson distribution is a discrete probability distribution. So we call it PMF. And the PMF is the lambda k times exponential of the negative lambda divided by the k factorial. Okay, what is k factorial? K factorial is, let's say k equals to an integer. So it starts with 1 times 2 times 3 times ... to the k. And that is called k factorial. That is called k factorial. Okay. So this is the PMF for the Poisson distribution. And for the Poisson distribution, there is a very special property. The property is based on this PMF, we can show that the expected value for the y is equals to what? Is equals to lambda. Is equals, so here, lambda is the parameter in the Poisson distribution. Okay, so that's why it's a Poisson distribution with lambda is the parameter. So, and the expected value for the y is equals to lambda, plus the variance of the y is also equals to lambda. that is a very special property for the Poisson distribution. So the variance and the mean for the y, they both equals to lambda. Okay, so that's why I'm here using the log of lambda I. So you can see the link function g is log function of the expected value of yi, right? So that is here. Okay, that is this term. So this one is equals to lambda I by definition, because that is the property for the Poisson distribution. Okay, so the link function is log. Okay, so these are the three examples, are the and also three very popular GOM models. Okay, let's see some examples. Oh, before we see the example, let's this is the summary of advantages of GOM over the traditional OLS. So compared to the ordinary least square models, the GOM models do not need to transform the response variable to a normal distribution. And also the choice of the link function is actually independent to the choice of the random components. So we have much more flexibility in the GOM models. And we will see some examples. For the same type of distribution, we have multiple choice for the link functions. Like for the logistic regression, when the random component follows a binomial, logit is one of the options for the link function, but that's not only one. We can use probit link. We can use C log link. Okay, so there was multiple choice. So that gives us some flexibilities. And the GOM models are fitted through the maximum likelihood approach. So the maximum likelihood approach is more general. And the maximum likelihood approach has lots of theoretical supports, like the asymptotic distribution for the parameter, estimated parameter follows a normal distribution, and the ratio of the likelihood follows some chi-square distribution so that we can do some hypothesis test. So there are lots of theoretical support and that we can use to simplify the statistical inference, okay, like the confidence intervals hypothesis test, which we will see that in a minute. And all the inference tools and the model checkings for the GOMs, they are all the same. They are the same. So that's why we need the random component follows an exponential family. So that unifies the inference approach and the diagnostic approach. So we will see some example to use the word test and likelihood ratio test to test the models and to compare the models. Okay, and there's often one procedure in a software to capture all the models. So we don't have, so that means we only need to use one function to do all these generalized linear models. We don't need to use one model, one type of model, use one function, just one procedure that applies to all the model types in the GOM. Like in the R, we use the GOM. For the SAS, the GEM mode. Okay, now let's see some examples. The first one is the Space Shuttle Challenger O-ring data. So this data set contains 23 previous shuttle mission experiment results. Okay, so we have the temperature, and we have the failure of the experiment from these 23 experiments. Okay, and the launch temperature on the day of the crash was 31 Fahrenheit for the Space Shuttle Challenger. Okay? So this data set is in the library far away. So the data set name is O-rings, and this is the data set. We have two columns, the temperature, that's the temperature of the experiment, and the number of damages from 6 experiments for each row. Okay, so you can see when the temperature is 53, we have 5 damage out of 6 experiments. Okay, so now let's first fit a logistic regression. Okay, so to fit a logistic regression, so first you can see the outcome is a binomial. So the response variable is a binomial. The number of damage is a binomial distribution. So what is a binomial distribution? Binomial distribution is based on a Bernoulli trial. So for a Bernoulli trial, for each Bernoulli trial, it has 2 possible outcomes, either 0 or 1. Okay, and you can define what is 0, what is 1. Okay, so, and the probability, let's say, of being 1, let's say, is P. Okay, so what is binomial? Binomial is we can have several Bernoulli trials, and their results are independent, and the probability of getting 1 is a constant P, is the same for all the trials. Then the total number of success, the total number of 1 follows a binomial trial with 2 parameters. One is the total number of trials, and the second parameter is the probability of being 1 within each trial. So that is a binomial distribution. Okay, for the Bernoulli trial, we only have n equals to 1. So if n is 1, then we can call this is a Bernoulli trial. Okay, so we can see in this example, it's a binomial, right? And if we look at each experiment, it can only have success or failure, damaged or not damaged, right? So you can see each experiment, it follows a Bernoulli trial, and for each row, it's a binomial. Okay, so here we can model the number of damage through the logistic regression. Okay, and one way we can model that is we can use the C-bind that's combined 2 columns. Okay, so the first column is damage, and the second column is not damaged. And as I said, for each row, that includes 6 experiments. Okay, and here the damage shows the number of damage out of these 6 experiments. So combine the damage and the 6 minus damage. That means what? One of the column is number of damage among these 6 experiments. Another column is the number of not damaged. Okay, so that is the response information and modeled by the temperature. So we need to make sure the software know that we want to have a logistic regression, right? So that's why in the family statement, in the family option, we need to specify this is a binomial, okay? But make sure that we also need to specify the link because the response variable is binomial. That's very useful. But remember, for the binomial response variable, logistic regression is not the only one. We can have some other choice, like a probit regression. That also applies to the binomial response. So you need to make sure the link function you need to specify. So the link function is logit. So you can see within the binomial, link equals to logit. And then you may ask, what if I didn't specify the link is logit? That's fine for the logistic regression because the default, if you don't specify the link is logit, you only specify the binomial without the link is logit. It's still using the logit because the logit link is the default. But if you want to use some other link function for the binomial response, then you have to specify it explicitly. Okay, but here just show you an example. And data set is the O range. Okay, so that's how you program in the R. So then we have the summary statistics for the fitted model, and you can see it. This is the model parameters. Okay, so the intercept for the logistic regression is 11.6. And the coefficient for the temperature is negative 0.21. Okay, so that means what? So that means if we have, so here when we interpret, so that is related to the log odds. Okay, so when we interpret the slope in the logistic regression, we have to be careful. Okay, so here, if we want to interpret the slope, we say by 1 unit change, like let's say by 1 unit increase in the x. In other words, in this example, if the temperature increased by 1 Fahrenheit, by 1 unit, then the logit will, on the average, increased by what? Increased by beta size. Okay, so that's how we interpret. But the logit itself is kind of difficult to understand, right? What is logit? It's the log odds. Okay, so a better interpretation is that if we can take the exponential, that's anti-log. Okay, so we can interpret the odds directly. So in that way, so we have to first take the exponential of the beta. Okay, so after we take the exponential of the beta, then we say by 1 unit increase of x, the odds will increase or decrease by this amount. And that is a better interpretation. because the odds is easier to be understood. Okay. So here I plotted the results. Those dots are the observed proportions for the damage against the curve is the fitted probability through the logistic regressions. Okay, and this is the code that I used to do the plot. So you can see the logistic regression is nice because it fit the probability in a smooth curve. And although this curve is not linear, and that is because this is the probability curve. But the log odds or the logit is a linear function of the temperature. But when we represent it through the probability, it's not a linear function. Okay? Now we can compare the logistic regression with a different model. Here, the probit model. So probit model is almost the same as the logistic regression model. The only difference is the link function is different. So in the probit model, the link function is the inverse of the normal cumulative distribution function. Okay, so what is a normal cumulative distribution function? So here we know the PDF for the normal distribution follows a bell-shaped curve, and that's PDF, probability density function, right? And we also have a CDF. That's the cumulative density function. So what is that? So that for the normal distribution looks like here. It converges to 1. It converges to 1. Okay. It started at 0 and converted to 1. So like here, if let's just say this is a standard normal distribution, standard normal, the mean is 0, variance is 1. Okay. So when the mean is 0 at the 0, we have half. So at 0, we have 0.5. That's the area on the left side of 0. Okay, let's say here, this is, let's say 1.5. So what is this value? If you go to the vertical axis, so the height for this point is the area. Let's say 1.5 is here. Is the total area on the left side of 1.5. And that total area is the height for this point, and so on. So it will converge to 1, right? Because the total area under the PDF will be goes to 1, right? So that's the inverse, that's the link function for the probit model. It's the inverse of the normal cumulative distribution function, okay? So if we use the probit, so the model line, the model statement line is almost the same. The only difference is the link equals to probit. So then the R will fit a probit regression model. Okay, and you can see the intercept and temperature. These are the estimated coefficients. And compare with the logistic regression, they are quite different. Like the intercept, this is 11.6 and -2, negative 0.2. This is negative 0.1 and this is 5.6. So quite different. You may say, wow, these are different, very different models. But when we plot the curves, so these are the two, so the blue solid curve is the logistic curve fitted by the model, and the red dash one is the probit model. You can see for the curve, they look almost the same. And in terms of the prediction, and for the Space Shuttle Challenger launched, the temperature is 31, okay? And we see that the probability that having a damage is 0.99 for the logistic gradient. But for the probit model, is very close to 0.99. So you can see the predicted value are very close. Okay, so here, when we see these two models, they both indicate one thing is the coefficient for the temperature is negative. You see that? That's the logistic gradient. That's the probit. So these two models, they tell us one thing is what? When the temperature is higher, the chance of having a damage is higher or lower. When the coefficient is negative for the temperature, that means when the temperature becomes higher and higher, the probability of having a damaged O-ring is what? Will be lower because the slope is negative. In other words, when the temperature is lower, the probability of having a damaged O-ring will be what? Will be higher. Is that right? And look at the temperature that the Space Shuttle Challenger launched. It's at 31 Fahrenheit. 31 Fahrenheit. That's a very low temperature. And you can see that when the temperature is over 60, the probability of getting damaged is quite low. But when the temperature is close to 50, the chance of having the damaged results is very high. And look at the curve. It's the same, right? When we have the temperature is 31, so that means it is somewhere around here. The probability of getting a damaged is almost for certain. But when the temperature is close to like 60, it's less than 20%. And when it's over 70, it's even less than 10%. Okay, so that's the effect. That's the temperature effect. So the temperature lower actually makes the probability of having a damaged O-ring is higher. So that's how you interpret. Okay, and there are some other link function we can use for the binary response. Like here is the complementary log-log model. So which has the link function is this one. That is another option. So this just show you some example that even for the same distribution of the response variable, we can have multiple choice for the link function. So that's the flexibility for the GLM model. Okay, now let's talk about the statistical inference in the GLM. In the previous slides, we only talk about the model interpretations, right? How to interpret these coefficients. Okay. Now before we talk about statistical inference, we know that the GOM is estimated through the maximum likelihood estimation approach. Okay, and you will see that we will do the likelihood ratio test for the statistical inference model comparisons in the GOM. So you can see there's a common word which appears very frequently in the GOM. That is the likelihood. So what is likelihood? And what is the difference between the likelihood function and the probability function? Okay. Are they the same or are they different? Right? So probably most of you think maybe they are the same. It sounds like the same, likelihood and probability, but there are some difference. Okay, so let's consider a model, let's say like a logistic regression model or a probit model. So we have a model there, and we have a set of parameters. Okay, like for the previous example, let's say we just focus on the logistic regression. Okay, and we have the intercept and slope values. Okay, and also we have an observed data set. Okay, then based on the model that we chose, based on the logistic regression, let's say, we know that the chance of observing this data set can be described as a function of beta. Okay, and we can look at in two different ways. One way is that we can say this is a function of observed data for the fixed parameters. Okay, so what does that mean? So that means if we have this, the probability of getting this data set, given the intercept is 11.67 and the slope is negative 0.21, is a function. And that we can call it, this is a probability function. So probability function is given the parameters, what is the chance of observe this data set, observe these Y values. Okay, so that's one way to look at it. And another way to look at it is now given this data set, and we can view as a function of the parameters. And this is called likelihood function. So probability function is actually a function given the beta is fixed, given the parameter is fixed, the chance we observe the data. Okay, and likelihood function is in a different way. Is given the data is fixed, what is the chance of observing these parameter values? Okay, so you can see these are some difference between the probability function and the likelihood function in the statistics. And why we need to talk about that? Because that is how we optimize the beta. So here, the maximum likelihood approach is what? Is given this data is what we observed, right? Given this data set, we want to find the beta to maximize the likelihood. And this is exactly the likelihood function. We need to find the beta to maximize. So likelihood function is a function of parameters. And the likelihood ratio test is, now we have two models. Okay, so we have, let's say one model is a more complicated model, and we say this is a larger model. model with more parameters. Okay, what does that mean? That could mean, let's say we have 5 variables, 5 x variables. The larger model may use all the 5 x variables. So that's the large model. And we have the likelihood. Okay, so we have the L parameter. L stands for large. We have more parameters, and that's the corresponding likelihood. Capital L stands for the likelihood. Subscript L stands for the large. Then we have a small model. Let's say we only use 1 or 2 of the x variables here, okay, not all 5. That's a small model, so we have the LS. And what is the likelihood ratio test? Likelihood ratio test is 2 times the log of the likelihood for the large model over the likelihood of the small model. Okay, so that is the likelihood ratio test. So you can see it's a ratio of the likelihood, right? But we need to take a log and multiply it by 2. And why we need to do that 2 times the log? Because in this way, we can show that this statistic is actually follows a chi-square distribution under some assumptions. What are the assumptions? Under the assumption is the sample size should not too small, should sufficiently large, and the distributional assumption holds. For example, if these models are logistic regression model, we should assume so the binomial distribution for the y holds. This assumption holds. Okay. So in that case, this one should follow approximately a chi-square distribution with the degree of freedom is L minus S. L is the number of parameters for the large model. S is the number of parameters for the small model. Okay? And we can also use the word test to test if one or more parameter in a model is equals to a certain value. So a word test is more like a utility test that we talk about in the OLS. Okay? So there are 2 special models in the GOM. One is the saturated model. Saturated model is what? That's the most complicated, and we can also call the connected dots model. So that means it fits the data perfectly. It connects the dots. So the saturated model is the model that gives the best results on the training data. Not necessarily the best model, but the model that perfectly fits the training data, but may not perfectly fit the testing. Okay, so that's the saturated model. And another model is called the no model. What is no model? No model means it doesn't use any explanatory variable in it. It only used a constant. So that's why the no model is also called the intercept only model. Only has a one constant intercept. Okay, so these are the 2 extreme models. This is like the most complicated model, fits the data perfectly. And that's the simplest model that only use a constant without any explanatory variable. And usually the best model, the optimal model is somewhere between these 2 extreme cases. Okay, so now there's a very important concept in the GOM that's called the deviance. So what is a deviance? So deviance measures how good the model fits the data. So it's like a residual sum of squares or the SSEs in the regression models. But deviance is better than the residual sum of squares or the SSE because deviance is more general. It includes the RSS or the SSE as a special example. Okay, so the deviance is defined by 2 times log of LS over L0. You see that this is very much the same as the likelihood ratio test. You see that? But here, what is the complicated model? It's a saturated. So deviance is always compared with the saturated. Okay, over that model. Okay, so for a particular model, model 0, the deviance is the likelihood ratio statistics that compare this model, model 0, with the saturated. Okay, so here the subscript capital S means the saturated model, not the small model. Small model is the lowercase s, but here is the uppercase. Okay, so based on now let's say if we have two models, a large model and a small model, you see that's a lowercase s. The likelihood ratio statistic is what? Can be re-expressed through the deviance, isn't it? Then this is the deviance for the small model minus the deviance for the large. And you may say, wow, there's a mistake. It should be the deviance for the L minus deviance for the S. No, that's not a mistake. Because here, if we rewrite it, you can see what is the deviance for the DS. This one is equals to what? This one is, if you check the deviance definition, is the 2 log what? L saturated over L lowercase minus the 2 log of the LS over the LL, right? Then if you do that, you will easily see this one is correct, okay? Because here, our model is in the denominator, okay? So that's why when we calculate when we do the likelihood ratio test, it's actually the deviance for the small minus the deviance for the large. And that makes sense because which one is larger? Deviance for the small model or deviance for the large? Of course, this one is larger. Why? The small model means the simpler model, of course, like a regression. If a simpler model, of course, have larger SSE, larger residual sum of squares, right? So it's DS minus the DL, okay? And here in this example, you can see the no model is this one, and the residual deviance is this one. So what is the no model? What is the no deviance? No deviance is the saturated model over the intercept only. And that's the, so is the deviance between the saturated model and the intercept only model, okay? And the residual deviance is the likelihood ratio statistics compares the saturated model with the temperature model. Okay, so the temperature model is the logistic regression that we are fitted here. Okay, so you can see the deviance, that's the residual deviance for the model is 16.91, that's the residual deviance. Okay, and the degree of freedom for the residuals is 21. Okay, so you may ask, so why we need to do that? Because here we can, if we know the residual deviance and we know the degrees of freedom for the residual deviance, then we can do some test, like a likelihood ratio test. Okay, so to do the likelihood ratio test, we just need to compare with the chi-square, right? So in the R, the p-value for the chi-square distribution is available in the p chi-square, this function. Okay, so that shows the probability for the under the chi-square distributions. Okay, so here we have the residual deviance. This one is the 16.91. Okay, so this one is 16.91. That equals to this one. Okay, and degree of freedom is 21, right? That's 21. And we want to find the p-value. So the lower is f. What does that mean? So that means when we have a chi-square distribution like that, we need to know the p-value which is on the right-hand side. So lower is f, means we don't want the probability on the left-hand side. We want the probability on the right-hand side. That's the p-value, okay? So you can see the p-value is 0.71. Okay, what does that mean? So when we interpret a likelihood ratio test results, you have to know what are the two models that we compare. Okay, so here, the likelihood ratio test, we have two models, right? Large model and a small model. Okay, so here, what is the residual deviance? So we are doing the likelihood ratio test based on the residual deviance. So what is the two models that we compared in the residual deviance? The first one is the saturated model. And that's the most complicated model, passing through all the dots. So that's the perfect model, most complicated. Okay, and compared with the temperature model, that's the logistic regression that we are fitted. We use the temperature information to predict the probability of damage on the O-ring, right? So you can see when the p-value is 0.7, right? Which is not significant. So that implies what? That implies there is no significant difference between these two models. In other words, our logistic regression, simple logistic regression only includes temperature. That is no significant difference with the most complicated model. So that means our model fits the data adequately well, right? What about the intercept only model? If we want to see if this is a good model or not, then we should use what? We should do the chi-square test. We should do the likelihood ratio test using the chi-square for under no deviance. Because no deviance is the likelihood ratio test between the saturated model and intercept only model. Is that right? So then I run this is the no deviance. Okay, this is no deviance, 38.9. Remember, 38.9, that's the no deviance. Okay, so this is the no deviance, 38.9, and degree of freedom is 22. So the degree of freedom for the no deviance is 22 degrees of freedom. You see that? Okay, so I run the test on the chi-square test. 0.14. So this is less than 0.05. That means there's a significant difference. Okay, so there's a significant difference between the intercept only model and the saturated model. Okay, and we can also compare with the intercept only model with the logistic model, or with the logistic regression with only the temperature included, right? So then we can just do the chi-square test on the no deviance minus the residual deviance. Okay, remember the no deviance is using the intercept only model minus the residual deviance. So that is comparing the temperature model with the intercept only model. You see that? So that is okay. So we see the then the degree of freedom is 1. Why it's 1? Because if you see that the degree of freedom difference between these two models is 1. This is the known model. This is the temperature model. So you can see the degree of freedom is 22 against 21. So there's only 1 difference. And that makes sense because the only difference between the intercept only model and the temperature model is we added 1 variable, that's temperature. So the degree of freedom should be 1, right? So that's why here I'm running the chi-square. That's the likelihood ratio test statistic. Degree of freedom is 1, and you can see the p-value is highly significant. So that means we can see there is a significant temperature effect. Okay, and then no model and our temperature model, there's a significant difference. And that means that there's a significant temperature effect on the probability of having a damage on the O-rings. Okay, and we can do the similar for the confidence intervals. For the confidence intervals, we can do it in 2 ways. One way is the simple way, that's the word, that's based on the word test approach. So word test approach assumes these estimated parameters, okay, follows a normal distribution with the standard deviation is the standard error here. So then we can calculate the confidence interval by what? Like if using the word test approach, we can calculate a 95% confidence interval on the temperature slope is what? It's just a negative 0.21, that's our point estimate, plus minus, because this follows a standard normal, okay? This follows a standard normal, so it's 1.96. That's the critical value we should use, okay? That corresponds to the 95%, okay? If it's 90%, then it's 1.28, okay? Times the standard error here, used here. So it's 0.053, okay? So that gives 95% confidence interval. But that's the word test approach, which is okay. But word test is an approximation, okay? There are some criticisms using the word test approach. So a more formal approach is using the profile likelihood. Okay, so profile likelihood approach is based on the maximum, is based on the likelihood. Okay, so trying to find an interval that includes 95% in terms of the likelihood. Okay, so that approach, and that cannot be easily calculated by hand. So instead, you can just use a function here. There's a function called a conf_in. And this function is in the mass library. Okay, you can do the conf_in for the fitted model, and it will show you the fitted profile likelihood-based confidence interval. Okay, and there is a option here. By default, it will show the 95%. But if you change to 90%, that's also fine. Just look at the help menu for this function, and you will see there's an option for the confidence levels. So this is the 95% confidence interval based on the profile likelihood approach. So you can see this is slightly different from the word test. And which one is better? This is a better approach. Okay? So this is the inference. Now let's see another example. So this example here, the purpose for this example, I want to use the statistical inference that we just talked about to apply to the model selections examples. Okay, so this is a esophageal cancer example. So in this study is a case control study. We have 88 combination of the age group, alcoholic group, and the tobacco consumption group. We have their number of cases that have the cancers, number of control that they don't have cancers. So we have this data set in this ESOPH data set. Okay, so this is the summary. So we can find the age, alcohol, and the tobacco consumption effects on the cancer rate. So we can use the logistic regression. So the response variable, we have the case controls. So we just use the C bind, N case, and N controls. N case are the number of cases that have the cancers. N controls are the subject that have no cancers. And use the age group, add the alcohol group and the tobacco group. But for the alcohol and the tobacco group, I used a star here. So that means we include the main effect for the alcohol and the tobacco consumption, as well as the interaction between the alcohol and the tobacco consumption. Okay, and the family is binomial. I didn't specify the link. So that means I will just use the default link, which is the logit. Okay, so this is the fitted models. So you can see the first one is intercept, right? The next few lines are the age group main effect. And the next few lines, next 3 lines are the main effect from the alcohol consumption. And the next few lines are the tobacco effects, main effect. And the last, these lines are the interactions between the alcohol and the tobacco. Okay, so we have the deviance, no deviance, residual deviance, and then I can fit it an additive model. That means we have the age, alcohol, and tobacco effect, but all these effects are additive, no interaction between the alcohol and the tobacco. Okay, so these are the model outputs. And I want to see if we need to use if there's a significant interaction effect between the tobacco and the alcohol. Okay, so what we can do is we can use an ANOVA function, which is doing the likelihood ratio test between 2 models. Okay, so the first model is the reduced model. That is the one is the additive effect. See that? Okay, so the first one is the reduced model. That's the one without interaction. The second one is the model.4. That's the one with interaction. Okay, so it will show you this is the degree of freedom between these 2 models. There are 9, and this is the deviance between these 2 models. Okay, and then you can we can run the test. Actually, there's an option here, can also show the p-value. But here I'm just showing what is the critical value for the chi-square with 9 degrees of freedom to get 95%, which is 16.9. So that means if the deviance is greater than 16.91, then it is significant. If it's less than 16.91, that means it's not significant. So obviously, in our example, there is no significant difference between these two models. So that means what? Interaction is significant or not? Is not significant, because the model 1, which only consider the main effect, is not significantly different from the model 2, which considers interaction between the alcohol and the tobacco. Okay, so that means that give us some confidence to use the first model, use the main effect model. Okay, and this just shows some side-by-side box plot for the in terms of the alcohol consumptions, tobacco consumptions, and age groups for the probabilities of getting the cancers. Okay. Okay. I believe this is our last example. Okay. For this example, we have there were 30 Galapagos Island, and we have 7 variables in this data set. And this data set is also in the library far away. And the relationship between the number of plant species with several geographic variables is of interest. Okay, so here we want to model the number of plant species through a bunch of explanatory variables. So obviously the response variable is a count variable, right? So we should not use logistic regression because that's not binary. And we should consider like a Poisson. Okay, so Poisson regression, of course, is a choice. But there are some other choice like a negative binomial. Negative binomial is similar to Poisson, but it's more complicated than Poisson. Actually, Poisson regression can be considered as a special case. Okay, then you may ask why we need to have the negative binomial, because this has one extra parameters to model the variance. Okay, one of the restrictions for the Poisson regression is what? I think I mentioned before, the expected value for the y is equals to what? Is equals to lambda, and also equals to what? The variance for the y. So that's actually a very strong assumption. That means the expected value of counts is equivalent to the variance of that variable, variance of count. So that is a very strong assumption, which may not be the truth in practice. Okay, if that relationship, if the expected counts is not equivalent to the variance of count, then that is called over dispersion or the under dispersion case. What is over dispersion? Over dispersion means the variance is greater than mean. Under dispersion means the variance is less than mean. And most of case is over dispersion. Okay, so that actually, give us, so that's the reason why we need to consider the negative binomial as a tool sometimes. Because if the Poisson regression does not hold, that assumption, which mean and variance are the same, does not hold, we may consider using the negative binomial because we have an extra parameter to model the variance. That means for the negative binomial regression, variance is allowed to be different from the mean. Okay. Another possible choice is called the zero inflated regression model. Okay, so sometimes people call it ZIP model. ZIP model is zero inflated Poisson regression. Okay, what is the zero inflated? regression model. This is very common if we observed excessive zero counts in the data set. If that is the case, we may model the data in two parts. One part is we model those excessive zeros. Another part is to model the rest of the data points. Okay, just like a two-step model. Okay, so that's called zero inflated regression models. And another one is the OLS model. This one is not recommended, but people still likes to use that sometimes because this is very simple. But this one will cause lots of troubles for the interpretations. And sometimes it cannot be applied because when we use the OLS for the count data, usually we take the log transformation on the Y. But if we have zero counts, that may cause some trouble. But if you still want to use that, then we usually use the log of Y plus 1 instead if we have zero counts. So in that way, we can avoid the problem caused by zero counts by adding 1. Okay, so but this one is not recommended, but still, this is simple. Sometimes people likes to use this. Okay, let's see. First, we use the Poisson regression on this data set. So the response variable is the species. That's the number of plant species on the island against all the other variables are used as explanatory variables. Okay, and the family is Poisson. And if you specify the family is Poisson, by default, the link function is log. Okay, so you don't need to specify the log as a link function. So this one, the intercept, so these are the estimated coefficient. We can see that some of the variables are significant. You can see those significant variables have those stars. Like 3 stars means the p-value is less than 0.001. And 2 star is between 0.01 and 0.00, and so on. But some of the variables are not significant. Okay, and the proportion of deviance that explained by the model is what? So you can see the no deviance is this one, and the residual deviance after adjusted by these variables is this one. So we can find 1 minus the residual deviance divided by the no deviance. And that is 0.911. So this can be used as like an R-squared statistics in the OLS. So this we can say, okay, that means about 91% of the deviance can be explained through these variables. Okay, through these through the models. And here I'm plotting some diagnostic plot. Okay, so the left panel shows the half normal quantiles, and the right panel shows the relationship between the mean and the variance. The horizontal one is the mean, the vertical one is the variance. Okay, so the half normal plots on the residuals, it shows the if there it can help us to it's like a normal probability plot to let us see if there's any extreme outliers. So we do see some outliers like this one, but it's okay to just see 1 or 2. Okay. So here we basically just see 1 potential outliers here, and this one is showing the mean and variance. Remember, for the Poisson regression, mean and variance should be the same. Okay, so this blue dashed line is the curve that shows the mean and variance are the same. If mean and variance are exactly the same, all the points should fall exactly on the line. But you can see here, we do see some trend for the mean and variance. When the mean increases, the variance increases, right? But the mean and variance, there's a obviously the variance is usually larger than the mean because most of points are above this line, right? So we see some over dispersion problems, okay? And actually we can calculate the dispersion parameters by ourselves. If in the ideal case, the mean and variance are the same, then the dispersion parameter should be 1, okay? How to calculate that? We can compare the sum of residuals for the sum of squared Pearson residuals, okay? So here, there was a few types of residuals. Pearson's residual is one of type. To find out the dispersion parameters, we need to have the sum of squares for the Pearson's residuals over the model degrees of freedom for the residuals. If the ratio is close to 1, that means there is no problem. Okay, so the Poisson model assumption holds. But here we see it's about 13. So that means there are some over dispersion problems. So what we can do is, let's try the negative binomials. So unlike the Poisson distribution, negative binomial assumes the mean and the variance have that relationship. So you can see the variance is not just equals to mean. It also have this additional part. Is the mean variance equals to mean plus the mean square divided by k. Okay, so if the k becomes larger and larger, let's say if k goes to infinite, then the mean and the variance are the same. So you can see Poisson regression is nothing but the negative binomial when the k goes to infinite. Oh, I'm running out of time. You know what? Let's stop here, and I will finish that tomorrow, next time. Okay? Any questions? Okay, if we don't have any questions, let's stop here.